Lesson 54. Lesson 54. Australian teenager Felix Zemdegs, at the age of 15, held 11 different records for solving a Rubik's Cube, including solving a Rubik's Cube in 2015 by 4.73 seconds, which is insane. Just pointing that out. That record since then, because that was 4 years ago, has been broken, I think, a couple of times. He's no longer the holder of that record. He is still a holder of having the fastest one-handed solve, which I think is pretty impressive, but he's not there. And yeah, but the question that I've got for you guys is, does anyone know what, like, why would I be talking about Rubik's Cubes for lesson 54? Does anyone know what 54 has to do with Rubik's Cubes? Oh, was a guess. Who guessed it? The number of thingy. Okay, what thingy? The number of what? The number of little cubes? Well, let's think about it. That makes the bigger cube. All right, well, let's think. If you've got 3 cubes in a face, you got 3 times 3, you got 9 cubes in one. Then you got another one which has got another 9, and then you got another one which has got 9. If you add all those together, that gives you 27. That's not 54. Does anyone have another? I mean, if you double 27, you can get to 54, but that's not why. That's not what this has got to do with. It. Does anyone know? On all those 6 faces, though, yeah. So here's the idea: it's not the little cubes, it's the stickers. If you add up all of the stickers, because there are 9 stickers on each of the faces, if you add up all the faces, the stickers, 9 times 6, you get 54 stickers. That's what I meant. You said, don't you do, Adri, don't you gaslight me. I can, because you know what, I can actually go back up and say, the number of things, the little cubes. Not little cubes, you mean little squares, or little faces. Yeah, I'm on to you, Adri. Give you anyway. Let's leave Adri alone, and let's talk about what the lesson goal here is. Lesson 54: applications of linear programming. We will be able to apply our knowledge of linear equations to solve problems. Now, so we've sort of already been using looking at applications of linear programming. When we started, we did lesson 53, where we looked at linear programming on Tuesday. What we did there is we sort of introduced this new idea called the objective function. And the objective function was to try and make your values as large or as small as possible. The limits on this function are your constraints. I did an example where I talked about a burger shop with like managers and team members, and you want to try and maximize the amount of money that you get. So the best way for you to maximize that amount of money is to figure out, well, what are the possible arrangements that you could have. What I did was I actually created this graph here. This graph here is just like, you would have a section here called the feasible region, which is this region here. You want to maximize the objective function. You want to maximize your profits in that region. And if the best way to do that is looking for the corners, maximize or minimize. And these corner points are the points that these corner points are the points that you care about. They're the points where the maximum and the minimum occurs. So in this case, the maximum and the minimum occur at this corner point, or this corner point. Some of you are saying, what about this corner point here, sir? And this is where an interesting line. That's actually not technically a corner because there's a dotted line on it. So you can't actually get to that corner. And I found that out. This is actually only a fact that I found out at the end of last term, at the end of last year, when teaching this topic. It's like, oh, well, why is this not the answer on the test? Well, there was a test question that was like that. I was like, oh, because that's actually not a corner. Same for the one at the top. And I thought that was really interesting. But yeah, those are the only corners that we care about. And again, so that was what we talked about. We talked about objective function. Objective function, oh, by the way, these were the, those at the top right were the constraints that I put on this function. So I said, for example, there has to be more than one manager, right? There has to be either one or more managers. You can't run a shift without managers. I said, there can't be more than 10 people in the shop because it's a pretty small shop. So that's why that line, this line here, the dotted line, that's that there. I said, well, there needs to be, for every 4 team members, there needs to be a manager. So then that stops it getting out of control. I don't want there to be 20 people and like only one manager. That would be a bit crazy. The last one I said, you need to have at least 2 people in the store. You can't just have one manager. That you need to have more than 2 people. And that gives you this thing here. We could actually then use a constraint. We could actually then start looking at this function here and looking at the corners and starting to figure out, well, what is the cheapest way that we could staff the store? My guess is the cheapest way to staff the store is probably going to be this one here, having one manager and one staff member, because I reckon that's going to be the cheapest. I think that's going to be cheaper than having 2 managers or having, but you know, I'm not sure. We'd have to actually run the numbers to find out. So that gives us this idea of an objective function. An objective function is like we've already done constraints before. We've already done created these type of graphs with one, even more lines to create a feasible region. Objective function is the new thing here. The objective function is, well, if you're in this zone, if you're in this feasible region, which part of this area do we want to be in if we want to make a function as big as possible or as small as possible? And that's really useful because sometimes you might want to maximize profit. Sometimes you might want to minimize costs. If you've got a certain amount of food, you may want to maximize how that food gets, baked into recipes rather than, or you might want to minimize the amount of waste that comes out. And so that's what these functions are for. We did an example where we constructed this, we constructed these, and we use the objective function to sort of start to graph it. What we're going to do for today's lesson, so I thought we'd do 2 things. But I would love to do 3, but I don't think we're going to get time to do this one, especially as we only have 20 minutes left. What I would like to do is I'd like to do this question here, which is just going to be very similar to the question we just did before. I want to find the corner points of these 2 lines, which means I want to find the intersection so that we get an idea. And then what I want to do is I would like to take all of these constraints. There are 1, 2, 3, 4, 5, 6 constraints. I would like to use them to construct a feasible region. We're not going to actually spend any time today doing an objective function for that feasible region, but I want to be able to construct it, give you guys some more practice, and also I want to teach you guys how to take a worded constraint like this. Even though I've talked to you guys about this already, I want to go back over and take a worded constraint like this and turn it into a linear inequation. So let's start from here. So as I've told you guys already, if I gave you guys a linear graph, which we're just going to do roughly something like that, and then we're going to do, I don't know, something like this. If I was to give you, and if I was to tell you for this linear equation that this region down the bottom was our feasible region, we would end up with 4 corners. 1, 2, 3, 4. This one is 0, 0. I don't even need to do it. This one and this one we could find from the intercepts, but this one we can only find by looking for the intercept between these two lines, which happens to be the solution for those two lines. Now, there are many ways to find out the solution of a simultaneous equation. Just as a reference, the two of them are elimination and substitution. What I'm going to do for you guys now is we're going to go through this one, and this one's going to be even easier than the one that I did earlier. So if I look at this one, we've got a positive x here, we've got a negative x here. We don't even need to do anything, right? Let's just rewrite 2 as being negative x plus 2y equals 4. You can see that the negative and the positive x. So if I take 1 and I add 2, that's going to give me negative x plus x. They're going to cancel. Then I've got 2y plus y. That's going to give me 3y equals 20 plus 4, 24. Y equals 8. And therefore x is x plus y equals 20. That's going to give me y equals, x, whoopsies, x equals 20 minus 8 equals 12. So that means the coordinates of the corner point, or the intersection of those two, are 8 and 12. Now, when I drew this, I was trying to actually get a rough idea of what this graph might look like. And so that would actually be, make this point here.
Sir.
Yo.
It's the other way around. It's 12 and 8.
Oh, thank you. You're so right. You are so right. It is 12 and 8. Yeah, good. So that's supposed to be a roughly like 12, 8. Now, as for the other points here, well, this line here, I can tell you that this point here will probably be 20. The reason I know that is because I know that, whoopsies, I know that this line that goes top to bottom here is 20, 0, and 0, 20. I know that because that is actually the plot of this graph here. Now, the other one, of course, is going to be probably 2y equals, if I just quickly change this one, 2y equals 4 plus x, and then for y equals 2 plus x on 2. So therefore that one here is going to be 0, 2. But yeah.
Sir, I have a question.
Yep.
How would you find the feasible region if those equations are linear equations and not inequalities?
Well, you wouldn't be able to.
So
because these are linear equations, not linear inequalities, you couldn't actually find the feasible region. I know that I've said the feasible region here, but in reality, you wouldn't be able to do this because it doesn't say greater than or equal to. You don't know which part is important. I'm just sort of taking these two equations to the next level to give you guys an idea of how would you go about finding these particular points, these particular corner points, and just re-going over the elimination method.
Okay, thank you, sir. I was just confused.
Yeah, that's all right. I 100% say. Technically, what I'm doing here, I'm actually plotting this graph here, less than or equal to 20 and less than or equal to 4. Technically, that's what I'm doing. Now, one thing I should point out though is that this is not the only way to solve a linear to find the corner point. This is not the only way to solve a linear equation. You could instead, if you really wanted to, taking equation 1, whoopsies, taking equation 1, you could change that to x equals 20 minus y, and you could use the substitution method. You could substitute that into equation 2, which would give you 2 times, in this case, 2y, sorry, whoops, I we've got a mistake there too. 2y minus 20 minus y is equal to 4. And then simplifying that gives you 2y minus 20 plus y equals 4. And then that gets you the same point. If you don't believe me, 3y equals 24, y equals 8. And then, yeah. So you can do it via substitution if you want, but you don't have to. So that's what makes, as I said, I warned you guys a little bit, this topic is one of the harder topics in my opinion, because you need to remember not just the topic that we just, not just this topic, but the topic we just did. So if you're not comfortable with, if you weren't comfortable with simultaneous equations from last topic, you're in a bit of trouble, because that's one of the ones we're going to, you need to be comfortable with for this one. Now I've got about 10 minutes left, so I'm going to try and tackle this question here. Now there are lots of bits of text here, and I'd like you to write these bits of text down first. And then what we're going to do is we're going to plot this graph. I'm going to, yeah, and the plot takes up more than graph. So we're going to go through these constraints first, but I would like you to jot them down. And then what we're going to do is we're going to try and find a way that we can write down these constraints. Oh, what are these constraints for? So what's the context of this question? You are the editor of a magazine, and your magazine has some very strict guidelines with regards to sexism and people on the front cover. Maybe that's what we're gonna say. We're gonna say that, you know, and these kind of things sort of are occurring a lot, you know. I don't think many people would explicitly write them down, but I'm sure there are companies that do, and they're like, oh well, no, this is a picture for the magazine. We have to make sure the magazine needs to at least make sure that there are this many people of color, this many people, this many women, this percentage of men, this percentage of women at least, blah blah blah. And I'm sure there are weird rules like that. At least, you know, I hope so. Well, I hope there is some sort of consideration of that, but you know, yeah, I don't necessarily 100% know. I know that I'm the website coordinator, and I know sometimes people say to me, "It's like, well, you've got to make sure that the front page of the website at least has, you know, some people of color or make some students of color, so that we can show how diverse we are." I'm like, okay, but yeah, it's an interesting, yeah, I sometimes feel like it's a bit fake. I feel like we shouldn't have to be worried about these things. They should just happen naturally if we were a good society. But yeah, let's not get into politics at the moment. Let's talk about this. So there has to be at least 2 women on the front cover, but there also has to at least be 1 male on the front cover. Okay, cool. So that means that pretty much also says, by the way, if you look at those first 2 constraints, there has to be 3 people on the cover at smallest. It must be less than 10 people on the front cover. I mean, that makes sense. If you've got 10 people on the front cover, you're probably not going to be able to see all of them, unless you've got like the cast of like I don't know. If you've got the cast of something, then you can probably fit all of them on there. But like anything more than that, kind of not really. There's not much point to it. It must be at least less than 8 men on the front cover. Okay, apparently they don't want too many men on the front cover. They don't care about women, but not too many men. Then what must be at least one person on the front cover? Well, that makes sense. You don't just want the front cover to have no one on it. And there must be more women than men. Okay, so maybe this is like, I don't know what type of magazine this is, that there has to be more women than men, but yeah, that happens to be the situation. So how do we turn all of these things, all of these weird constraints into a graph? Well, what we could do is we could say we're going to use two variables. We're going to use M for men, and we're going to use W for women. So if I use M and W, right, there must be at least 2 women on the front cover. How could I write that as a constraint? I want you guys to give a guess in chat using M and W. How can I write that as a constraint using M and W? What do you guys think? Go ahead.
Sometime.
M and W, people. How could I write there must be at least 2 women in using M and W as our variables? M meaning the number of men.
W is more than or equal to 2.
Good. That's exactly how I would do it. So number of women. So therefore, W must be greater than or equal to 2. The number of women must be more than 2. What about this next one down? There must be at least 1 male on the cover. How could I write that one?
M is bigger or no way. Oh, sorry. Is it like M is bigger or equal to 1? Yeah.
M is bigger than or equal to 1. Perfect. So they're the first 2. Now the next one becomes a little bit more challenging. There must be less than 10 people on the cover. How could I write that one? Does anyone know?
W plus M is less than 10.
Perfect. If I take W and I add M, so if I take all the men, all the women, and I add all the men, that has to be less than 10. I can't have that many people on the cover. So I could have, using these rules, I could have 9 women and 1 man. I could have 8 women and 2 men. I could have 7 women and 3 men, so on and so forth. What about this next one? There must be less than 8 men on the cover.
M is less than 8.
M is less than 8. Now we have to be careful here. It's not less than or equal to, it's just less than. Okay, there must be at least 1 person on the cover. I'll do this one. So at least 1 person means that we don't care about men or women. We don't care what gender they are. There just has to be someone on the cover. So if I take all the men and I add them to all the women, that total must be more than or equal to 1. Men plus women must be greater than or equal to 1. You might be saying, but it just says 1 person. But if M is 0, then W has to be 1. If W is 0, then M has to be 1. But there's one more condition in the bottom. There must be more women than men. How do I write that one?
Women is greater than men.
Women is greater than men. So yeah, W, the number of women is greater than the number of men in this situation. But yeah, let's see. Let's grab a look at the time here. Okay, I've not got time to actually. So what we're going to do next time, or what we would do normally, is then I would then say, right, cool. Now that we've got all these things, we can now plot them. And so what we would do is I go W and M, and then we would go through it, and we would plot them, and then we would go, okay, W has to be greater than or equal to 2. That means that if I do a line like this, I know that W has to be greater than this number. So therefore, that becomes W can't be less. You can't have one woman on the front cover, and so on and so forth. And then what we'll do is we'll build it up. We haven't got time to do that at the moment because I'm looking at the watch here. It says 9:48. So what I'm going to do is I'm going to leave that here, but we'll come back to this. What I would like you guys to do is to write down these constraints. I'm probably going to close this PowerPoint, and I might lose those constraints. So I need you guys to write them down so that when we come back to doing this on Tuesday next week, we can do it. I'm also going to warn you guys, but the last little thing is this. We're coming up to the end of linear programming now. The other Year 11 teachers and I haven't figured out what we're going to be doing, as if we're going to test you guys, how we're going to test you guys, if we're not going to test you. We haven't come up with that yet, but I am going to warn you guys that we are coming up to the end, so something might be happening soon. So if you haven't, and if you haven't been keeping up to date with the questions and stuff like that, I need you to make sure you upload those. That's about it for our time here today. You guys have an awesome weekend.